In this video, you will explore set relationships. By the end of this video, you will be able to use Venn diagrams to illustrate set relationships, determine the number of subsets of a given set, and apply De Morgan's laws. A Venn diagram is a graphical tool used to showcase how sets relate to one another. At its core, a Venn diagram is composed of overlapping circles or ovals. Each circle represents a different set within the context of our problem. Step 1 is all about identifying the sets in your problem and labeling them using different circles or ovals. Each circle represents a distinct set within the context of your problem. Moving on to step 2, once you've labeled your sets, it's time to place the elements of each set inside the corresponding circle or oval. This helps us visualize which elements belong to which set. Step 3 is where the magic happens. We'll illustrate the relationships between sets using overlapping regions. These overlapping regions represent the intersections and unions between sets. Now, in step 4, it's crucial to clearly label everything. Label the overlapping regions to indicate which sets intersect there, and label the individual circles to show which sets they represent. Today, we'll explore the significance of the intersection in a Venn diagram and how it relates to sets X and Y first. Let's clarify what the intersection in a Venn diagram means. It represents the elements that are shared or common between two sets. Now let's apply this concept to sets X and Y. In the context of these two sets, the overlapping region in the Venn diagram represents the elements that belong to both sets X and Y. Venn diagrams are remarkable tools for visualizing many aspects of set theory. They help us grasp set relationships, intersections, unions, subsets, and disjoint sets with ease. They simplify complex set operations, making problem-solving much more manageable. They clarify the connections between sets, helping us see what they have in common and where they differ. Today, we'll explore a fundamental concept: the number of subsets of a set. This concept involves understanding how many different collections we can create from the elements of a set. A subset is a collection of elements taken from the original set without considering their order. Today, we're going to learn how to calculate the number of subsets in a set. This skill is particularly useful in various mathematical and analytical applications. The first step is simple: count the number of elements in the given set. Next, we use the subset formula, 2 raised to the n, where n is the number of elements in the set. This formula helps us find the total number of subsets that can be formed from the set. If you ever add or remove elements from the set, you can still use the same formula. Just make sure to update n with the new number of elements to find the revised number of subsets. First, let's identify how many elements are in set D. Set D contains 3 elements, X, Y. To find the number of subsets, we'll apply the subset formula, 2 raised to the n, where n is the number of elements in the set. For set D, that's 2 raised to the 3rd power, which equals 8 subsets. Now, what if we add another element? Let's call it Y to set D. Our new set becomes D equals X, I, Z, Y. Using the formula again, we get 2 raised to the power of 4, which equals 16 subsets. Conversely, if we remove an element, like E, from set D, we get D equals X. See, applying the formula once more, 2 squared, which equals 4 subsets. To efficiently find the total count of all possible subsets, we use the subset formula, which is 2 raised to the power of n, where n is the number of elements in the set. This formula simplifies what could otherwise be a complex counting task. Adding or removing elements from the set has a direct impact on the number of subsets. It's crucial to apply the formula correctly when changes are made to the set. The concept of subsets is fundamental in various mathematical and statistical applications. It's vital in probability calculations, combinatorics, counting problems, and data analysis, where understanding subsets helps us make informed decisions. De Morgan's laws offer a way to express the negation of these complex set operations in a much simpler and more understandable form. They are a cornerstone in set theory, used to manipulate and analyze sets effectively. These laws specifically address the complement of unions and intersections of sets. They tell us how to find the complement of the union and intersection of sets. The beauty of De Morgan's laws lies in their power to simplify complex expressions. They help us break down intricate set relationships into more manageable and comprehensible forms. Let's start with the first law. The complement of the union of two or more sets is equal to the intersection of their complements. Symbolically, it's represented as not A and B equals not A intersect not B. Moving on to the second law. The complement of the intersection of two or more sets is equal to the union of their complements. Symbolically, it's expressed as not A intersect B equals not A and not B. Let's break it down into two simple steps. First, we start with the intersection of sets X and Y, which is represented as X intersect Y. Next, we apply De Morgan's law for the complement of the intersection. Symbolically, this is expressed as not X intersect Y equals not X and not Y. What this means is that the negation of the intersection of sets X and Y is equal to the union of the complements of sets X and Y. To sum it up, De Morgan's laws are indispensable tools for simplifying set operations. These laws allow us to simplify complex expressions, making them more manageable and comprehensible. They have broad applications and are a must-know for anyone working with sets in mathematics, logic, or computer science.